Hi guys, today we want to take a look at the ideal gas law. And much of this is a review of some things we've already done in honors chemistry because we've looked at the gas laws, we've looked at the ideal gas law, and we've actually also looked at Dalton's law of partial pressure, which is just really simple adding. Probably one of the new things might be the idea of a mole fraction. So, looking at the relationship between pressure, volume, and temperature, if you consistently remember that P1 V1 over T1 is equal to P2 V2 over T2, you will always remember what kind of relationship exists. So, volume and pressure, that's an inverse relationship. So, when one goes up, the other goes down. If we look at volume and temperature, again, P1 V1 over T1 equals P2 V2 over T2. So volume and temperature, if one is on top of the other, then that is a direct relationship. So when one goes up, the other goes up. When one goes down, the other goes down. The important thing to remember about temperature must be in Kelvin. And the reason for that is in order for the relationship to exist, in order to have the volume double when the temperature doubles, you need to use some type of a scale where the volume is 0 when the temperature is 0. And for that reason, we have to use Kelvin when we solve our gas law problems. Relating volume and temperature, again, P1 V1 over T1 is equal to P2 V2 over T2. Volume and temperature, that is a direct relationship. Now, if you increase the number of moles of gas in the system, you're actually going to increase the slope of the line. And that's just an important thing to keep in mind because sometimes on an FRQ you may be given a graph and some data is already graphed related to gas and volume and temperature. And then you'll be asked to predict what would happen if you had more or less of the substance. And so just remember that if you increase the number of moles of gas, the slope of the line will increase. If you decrease, the slope of the line will decrease. So just an important note to make there. Here's Avogadro's principle. In an Avogadro's principle, volume is going to be proportional to the number of moles. If you double the number of moles, you double the volume when the temperature and the pressure remain the same. So here's our friend, standard temperature and pressure, or STP. Standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. Well, normally, if you think even of our classroom, it's hopefully never 0 degrees Celsius, and the pressure is rarely 1 atmosphere. So that's when we're going to use the ideal gas law. But if we're at STP, an important thing to notice if you're doing an FRQ and they give you some data, but at STP, 1 mole of any gas will occupy 22.4 liters of space, and there will be a mole of gas particles inside, 6.022 times 10 to the 23rd. Now, be careful, because sometimes it's super tempting to use STP when things aren't at STP. So always kind of underline when data is given to you, when a temperature is given to you or a pressure is given to you. Take notice, is it at STP or is it not? Because when it's not, we're going to need to use the ideal gas equation. The ideal gas equation is normally used, and most of the time you have 3 of the 4 variables. This value for R is on your formula sheet, and there are several values for R, so you need to pay attention to the units that are being used. We have liters, we have atmosphere, pressure as atmosphere, we have Kelvin, and we have moles. So if we do an ideal gas equation, here we have an 8.5 liter tank. It contains helium gas at 16.9 atmosphere and 25 degrees Celsius. So the first thing to notice here is we are not at STP. So we're going to just make an inventory. We have a volume. Our volume's 8.5 liters. Our pressure is 16.9 atmospheres. And our temperature, at this point, I'm going to immediately convert it to Kelvin. 25 plus 273, so that I don't forget. So that's 298 Kelvin. And then we can use the ideal gas equation to solve for moles. So N is going to be equal to PV over RT. And then we can just plug and chug, really. We have 16.9 atmospheres. Always include your units, and I'm going to show you why in just a minute. 8.5 liters. I now have to pick a value for R from my formula sheet that deals with liters, atmosphere, and Kelvin. And that one is 0.08206. And even though it seems like a pain, write down the units. It's liter atmosphere per mole Kelvin. Then I'm going to do the Kelvin temperature. And the reason you should do your units is this is a great check for you now that A, you have set the problem up right, and B, that you have used the correct value for R. So I can cancel out my Kelvin, I can cancel out my atmosphere, I can cancel out my liters. I am left with moles. Now, plug this into your calculator. The next thing to ask yourself is, hey, how many significant figures does my answer have to have in it? So I'm going to look at the data I've been given. This one has 2, this one has 3, this one has 3. So your final answer should have 3 significant figures. So put this in your calculator now and see what you get. You should get 5.9 moles of helium. All right, example number 2. It says if all of the helium is used to fill 1.5 liters of red balloons at 0.99 atmosphere and 32 degrees Celsius, how many balloons will you end up with? Okay. Well, let's see. Let's use the ideal gas equation, PV equals nRT. Okay, all of the helium, we know how many moles of helium we have, so we know we're going to solve for a volume, and I'll show you why in just a moment. So we're going to do nRT, volume is going to be nRT over P. My volume is 5.91 moles because we just solved for that. I'll use R again, 0.08. I'm copying it from your formula sheet. Liter, atmosphere, mole, Kelvin. And then 32 degrees Celsius plus 273 is going to be 305 Kelvin. And I have 0.99 atmosphere. So I can cancel out my moles, I can cancel out my Kelvin, I can cancel out my pressure, and my volume then is 149 liters. So I have a total volume of 149 liters. Each balloon has a volume of 1.5 liters, and we want to find out how many balloons can we end up with. So I can take my 149 liters, and there are 1.5 liters per one balloon. And you should find out that you will get 99 red balloons. Oh, I think there's a song out there related to that. Okay, so 99 red balloons. Here's another one. An unknown gas is collected in an 850 milliliter vessel at 1.02 atmosphere and 23 degrees Celsius, not STP. The evacuated vessel has a mass of 138.45 grams and the vessel and the gas have a combined mass of 140.12. Yikes. Find the molar mass of the gas. Yikes. What do I do with that? Well, one thing, think about what you need to solve this problem. One thing you might be interested in is that molar mass, we'll call that big M, is going to be equal to mass divided by the number of moles that you have. So that's going to be the molar mass. So what do we need? What steps should we follow to solve this problem? What are we going to solve for? Well, if I have a mass, okay, an unknown gas, we have a mass, right? The evacuated vessel, we're going to be able to solve for the mass of the gas. And we can use the ideal gas equation to figure out how many moles we have. So PV is equal to nRT. Now, let's think about what we have. We have, so N is going to be equal to PV over RT. So N is equal to the pressure. We have a pressure of 1.02 atmospheres. An 850 milliliter vessel. Well, wait a second. My volume has to be in liters, so make sure we convert that to 0.8500 liters. R, I'm going to use 0.08206. And my temperature, 23, I have to convert that to Kelvin, 273. So I should get 296 Kelvin. All right, put this in your calculators and see what you get. I'm going to have 3 significant figures in my answer. Yep, 3 sig figs because of the 1.02 atmosphere. And after putting it in your calculator, let me give you a minute, you should get 0.0357 moles. Okay, we're not done yet though. That's not the molar mass of the gas. Okay, so step 2 is then molar mass is equal to mass divided by N. Well, the mass of the gas, look at the data you've been given. You've been given the total mass of the flask, so we have to do 140.12 grams minus 138.45 grams because you were given the evacuated vessel, so that's the vessel empty, and you were given the vessel plus the gas. So to get the gas, you have to subtract those, and then we're going to divide by our number of moles that we just solved for. And so you should find that the molar mass is 1.67 grams divided by 0.0357 moles. So the molar mass of our gas is 46.8 grams per mole. So look back through this example again because some of your homework problems will be like that, okay? Another example of some of your homework problems, here's an example. An unknown gaseous hydrocarbon has a density. Now remember, density is equal to mass over volume. So an unknown gaseous hydrocarbon has a density of 3.24 grams at 1 atmosphere and 28 Celsius. Find its molar mass. So we can use the ideal gas equation, and then for N, we can just put in mass over molar mass. Because if molar mass is equal to mass over N, then we can solve for molar mass by N would be equal to mass divided by the molar mass. And so we can kind of plug in that way then. Our molar mass is going to be equal to the mass. All right, we have a density of 3.24 grams per liter. And so we can use that density value. So that's our mass over volume. That's going to be our density. So we can do density over the pressure times RT to solve for the molar mass. So this is using some fun algebra to kind of rearrange an equation. You are often asked to do this on the AP exam. So remember, N you can use, you can also deal with molar mass. If you have a mass and a volume, you may see that as a density. So you'll get some practice on that with your homework. So kind of take a look at that. All right. Oops. Okay. So sorry, I kind of wrote over that. We can do this. We can do the unknown gases. So the molar mass of our hydrocarbon is equal to its density of 3.24 grams per liter, divided by the pressure. Our pressure is 1. I like 1 as an atmosphere because that's easy to divide by. And then we're going to multiply that by RT. R is 0.08206 liter atmosphere mole Kelvin. And then our temperature of 28 plus 273 is 301 Kelvin. Sorry, I'm running out of room. 301 Kelvin. And if we put all that into our calculator with 3 significant figures, you should find, so if I'll do 3.24 divided by the quantity 0.08206 times 301, or 3.2 times 0.08206 times 301, should get 80.0 grams per mole. Okay. This kind of walks you through it. Okay, 3.24 grams per liter, 1 atmosphere, molar mass is 80 grams per mole. The combined gas law, remember, you have to use Kelvin. If the pressure, volume, or temperature of a system changes, but the number of moles remains the same, you can use the combined gas law, as long as you promise me you will change your temperature to Kelvin. A cylinder of gas is kept at a constant volume. As the temperature increases from 24.1 Celsius to 32.4 Celsius, if the initial pressure is 1.01 atmospheres, what's the final pressure in millimeters of mercury? So what we can do here then is we have my favorite, P1 V1 over T1 equals P2 V2 over T2. And make an inventory. Go back. All right, cylinder of gas, constant volume. All right, the volume's constant. Temperature increases. T1, it's going to start out at 24.1 plus 273. So it's going to be 297.1 Kelvin. Whoops, Kelvin. And T2 is going to be 326.4 Celsius. 326.4 plus 273 is 599.4 Kelvin. And then the initial pressure is 1.01 atmosphere. And you're going to solve for the final pressure. So, using the combined gas law, we are keeping volume constant. So we don't need our volume here. We can just do P1 over T1 equals P1 over T1 equals P2 over T2, and we are solving for P2. And if you plug and chug, you can say that P2 is equal to cross multiply P1 T2 over T1, and then just plug and chug. So your pressure should be oops, I didn't do that right. Okay, pressure 2.04 atmosphere. And we were given, let's see if it asked us for millimeters of mercury. Yep, final pressure in millimeters of mercury. So using the atmospheres that we gave us, we had 2.04 atmosphere, then we can convert that into millimeters of mercury. There is a conversion on your formula sheet. So 1 atmosphere is 760 millimeters of mercury, so you should find out that you have 1.55 times 10 to the third millimeters of mercury. Dalton's law of partial pressure is wonderfully easy because Dalton's law of partial pressure says, hey, if we have a mixture of gases, the total pressure is the sum of the pressures of everything that makes it up. The big thing to keep in mind is make sure when you're adding all these pressures is that the units are the same. If they're all atmospheres, then you're adding all the atmospheres. If it's all millimeters of mercury, you're adding all millimeters of mercury. If some are atmospheres and some are millimeters of mercury, convert so that they are all the same unit. So here we have, if 100.8 grams of oxygen, 289.8 grams of nitrogen are pumped into a 6-liter scuba tank that is kept at 20 degrees Celsius. So first thing I'm going to do is take that 20 degrees Celsius and add 273 to it. That is 293 Kelvin. So just a note. So this is to find the partial pressure of each gas and then to find the total pressure in the tank. So what should we do? Well, step 1, we're going to find the partial pressure of the nitrogen gas. Well, we were given moles of nitrogen gas, or grams of nitrogen gas, so we could figure out how many moles of nitrogen gas we have. We can then use the ideal gas equation to solve for the pressure of nitrogen. So it's going to be the moles of nitrogen times R times the temperature over the volume. And so you can plug in the 10.34 moles, the 0.08, you can use 206 or you can use 21, the temperature of 293 Kelvin divided by the volume. So you should get the partial pressure of nitrogen as 41.5 atmospheres. What do you think step 2 is? Hopefully said, hey, find the partial pressure of the oxygen gas, right? How are we going to do that? We're going to take our mass of oxygen gas, convert it to moles, yay. Then we're going to use the ideal gas equation to solve for the partial pressure of oxygen. We now know the number of moles, R, temperature, and volume. And so we should find that the partial pressure of the oxygen is 12.6 atmosphere. And then to find the total pressure in the tank, what should we do? So find the total pressure in the tank. How do we find the total pressure? So total pressure is equal to all of the partial pressures. Well, there's only 2 gases in the tank, so we can add those 2 partial pressures to get a total pressure of 54.1 atmospheres. Last but not least, we will look at mole fraction. Mole fraction, and let me see if you have that on your formula sheet. You do not, so you're going to have to remember mole fraction. Let me double check. I'm looking at your formula sheet here. I do not see a mole fraction. So mole fraction should make sense. This is going to be when you have a mixture of moles, and it's the percent composition, so it's going to be a percent thing by moles of a single component in a mixture represented in its decimal form. Okay, so we're not going to multiply by 100. So the moles of whatever component you're asked about and the sum of the moles in the mixture. So this says find the mole fraction of each component in a gaseous solution that contains 6.7 moles of helium, 2.5 moles of argon, and 1.6 moles of chlorine. So we're going to have to find the mole fraction for helium. We will take the 6.7 moles of helium over the total. Well, let's quickly total them all up in our calculator. I'm going to take my 6.7, my 2.5, and my 1.6, noticing while I'm doing that these are 3 significant figures for answers. Okay, so that's going to be 10.80. And so then if I do my 6.7 divided by 10.80, I get 0.620. I need 3 significant figures. And that's the mole fraction for helium. My mole fraction for argon will be the part that argon is. 2.5 moles of argon, 10.8, that was the total. I'm going to do my 2.5 divide by my 10.8, and I get 0.231 for my mole fraction of argon. And then for my mole fraction of chlorine gas, I will take the part that chlorine gas is, moles of chlorine, over the total. That is still 10.8. And I get 1.6. I divide it by 10.8. I get 0.148 for my mole fraction for chlorine. This should add up close to 1. So if we do 0.620 plus 0.231 plus 0.148, I get 0.999, which is very close. You may also have a problem where you know the mole fraction and you know everything except for one component. And so you can use this principle. So I can show you an example of that as well. All right, here's a gaseous solution, and it contains neon, hydrogen, and helium. And it tells you the mole fractions of neon and hydrogen as 0.233 and 0.478, and you need to know the mole fraction of helium. Well, all of them should add up to 1, and so you can just have 1 minus 0.233 minus 0.478, and you will get a mole fraction of 0.289. You can actually find the partial pressures of any component in a gas mixture by multiplying the total pressure by its mole fraction. This is a super helpful situation. So the mole fraction of oxygen in a container at 0.97 atmosphere is found to be 0.210. What's the partial pressure? Yay! Partial pressure is going to be the mole fraction times that pressure. So that's super, super helpful. We would take 0.210 times the 0.97 atmosphere, so the partial pressure of oxygen is 0.2 atmosphere, which is pretty kind of cool. If we were all present, we could do the molar mass of butane, but we actually did this lab when we did the gas laws in honors chemistry. So collecting a gas over water, if you guys remember, you had a butane lighter and you bubbled it into a graduated cylinder filled with water. So when measuring the volume of the gas collected, you have to line up the water levels inside and outside the graduated cylinder. You guys had to do that, and that showed you that the pressure inside the cylinder was equal to the atmospheric pressure. So here we have a problem. A 0.129 gram sample of an unknown gas was collected over water at 25 degrees Celsius and 1.01 atmospheres. The collection cylinder contained 37.45 milliliters of gas after the sample was released. And then it gives you the vapor pressure of the water. Your total pressure is going to equal the pressure of whatever gas it is plus the pressure of the water. So that's why they've given you the pressure of the water. All right, so the first thing is we have some millimeters of mercury. So let's convert the units to atmosphere. We're going to take our 23.76 millimeters of mercury, And then I just use the conversion that 1 atmosphere is 760 millimeters of mercury. So now we have the pressure of the water. So for the total pressure then, finding the partial pressure of the unknown gas, the total pressure is going to be the pressure of the unknown plus the pressure of the water. We're looking for the pressure of the unknown. So we knew that our total pressure was 1.01 atmosphere. We just found out that the pressure of our water was 3.126 times 10 to the minus 2 atmosphere. So the pressure for our unknown is 0.98 atmosphere. So we have a pressure now, we have a temperature now, we have a volume now that we have to convert to liters, but we can solve for the number of moles. We can find the moles of the unknown gas. We have the pressure of the unknown, we have a volume, we have R, and we have T. So pressure, 0.98 atmosphere. Volume, they gave it to you as milliliters, so remember to convert that to liters. Our value for R, and then our temperature was given to us as 25 Celsius, so that will be 298 Kelvin. And so we can solve for how many moles we have of the unknown. Now remember, we can find the molar mass because our molar mass will equal mass over the number of moles. Well, we now have a mass. We were given a mass at the beginning of the problem. You were told that you had a 0.129 gram sample. And you know how many moles that is now. So now you know the molar mass of the gas. So your homework will reflect several examples of these types of problems. It's a lot of math in one lecture, but work through the problems carefully, and I'm always available for help if you need it. So thanks, guys.